Eventually, however, we had more and more trajectory data, and also it was possible to do experiments. So there were biologists who experimented in the area of swarm intelligence, and they thought, okay, why don't we make experiments with crowds of people? And this basically triggered off a new era in this field of traffic physics, we could say, or sociophysics. And the goal was basically to figure out the functional form of those forces, assuming it were forces, based on the data. I mean, making no assumptions about elliptical or not. And this is what we're doing over here. So they did experiments, and basically they first measured the movement behavior of single pedestrians. I can see that we put some table tennis balls on top of the shoulders. That helps to measure more accurately. So accurately that you would see actually the oscillations that go along with each stride. And then they continued. It was in the team of Guy Terola, by the way, in France. They continued looking at interactions, right? Interactions with standing pedestrians, interactions with moving pedestrians, and then there were even experiments with 3 people, and so on and so on. And eventually what you get is distributions of data depending on relative location. And that allows you to determine not only the frequencies of side choices. What you see, for example, over here is that, first of all, the right-hand side is preferred, as we observed before. But the preference is much more pronounced when both people are moving, as compared to a situation where one is standing and the other one is moving. So basically, there's a reinforcement effect if both are moving. So the symmetry breaking is much more pronounced. And it's possible also to determine the forces as a function of the relative location in space. And that then can be fit by mathematical functions. And these are the functions that I basically found. It was a superposition between 2 effects. When there was a head-on encounter, then basically people were decelerating. However, if it was more an approach from the side, then basically people were changing directions more than speed in order to kind of get a little bit away from the person. Okay, and those 2 effects are added on top of each other, and then you basically have a functional form that produces pretty similar forces and flow fields and trajectories. And as you can see over here, the average trajectory is clearly within the standard deviation around the measured trajectory. So that is a nice success, that the parameter calibration allowed to reproduce that. So that is called validation. If you then do something that challenges the model. We had another validation. We applied the very same model with the very same parameters to a real-life situation in, I think it was the pedestrian zone of Toulouse, I guess, if I remember well. And there we were predicting the distribution of pedestrians over this walkway. And you can see there's an asymmetrical distribution as expected if there's a side preference. and it's also pretty much reproduced by the simulation. Well, the simulation was, as I said before, not specifically adjusted to that real-life scenario. Okay, so in conclusion, that data-driven model worked pretty well. Now, the question is, what kinds of phenomena can these kinds of social force models be reproducing? So what we find is that the social force model will give us the lane formation phenomenon, right? So you can see this quite clearly in that movie over there, and also in the snapshot that has been separately produced many years back, actually, on the right-hand side. Now, at Bottlenecks, we actually find the oscillatory flow that we have also seen in the data. And so basically on one side, people are queuing up, and that produces increasing pressure, and that increasing pressure will stop the opposite flow and then turn the flow direction. This is how it goes back and forth and back and forth. It looks a little bit like there's a traffic light, but in fact there's none. And now we're looking into the maybe most famous pedestrian intersection of the world, which is located in Tokyo. Many TV shows have reported about it. And so here you basically have those crossing pedestrian flows that we've been talking about. Here is a simulation, and we'll in a few seconds see the phenomenon of stripe formation. And this stripe formation phenomenon allows pedestrians to walk forward and sideward. That means to cross the other stream without stopping. So it's really a self-organization phenomenon, an emergent spatial-temporal pattern of motion that allows those flows to cross each other without requiring pedestrians to stop. And with those observations of collective patterns of motion, we can actually improve pedestrian facilities, right? So for example, if you have 4 crossing flows, you would typically get a chaotic, unstable flow in the intersection area. But if you break down the intersection into 4 intersections of 2 flows, then we would find a stripe formation, and if we do it well, it would produce us a circular flow, because the stripes are moving forward, as I mentioned before, right? And these are just some examples. Typically, we would have the design elements on the left, corridors, bottlenecks, intersections, and all of them can be improved. It's maybe most simple to understand for the bottleneck case, right? We're cutting corners. That means reducing the available space, less is more, would actually improve the flow through a funnel-shaped design. So if taking space away can improve the flow, couldn't it also improve the flow in case of corridors? And the answer is yes. Here we have some pillars. That is actually in Budapest, Hungary. And another metro arrives, and suddenly there are people walking in 2 opposite directions, and then the 2 flow directions are separated by the pillars. The pillars stabilize the flows in a sense, and this is why it actually improves performance of the pedestrian facility. Now then we saw, okay, what happens if we put an obstacle into the center of an intersection? And surprisingly, again, it could improve the situation, because there are actually many possible collective patterns of motion. And one of them would be oscillatory flows, where first those 2 directions would dominate, and then in the next phase, those two directions would dominate, and back and forth. But there could also be circular flows, counterclockwise or clockwise. And so basically there are several different collective patterns of motion that would compete with each other and they would destroy each other. And putting an obstacle into the center would make the oscillatory pattern less likely and would support rotary flows. And then putting extra railings and considering the preference for the right-hand side in many countries, that would actually induce rotary flows in one direction here, counterclockwise, okay? This way we could actually improve performance of the intersection area, okay? Now, of course, most pedestrian facilities would be a lot more complex, and so the question is what to do about that. However, we can apply evolutionary algorithms where we start with the original design with another method that basically drops little obstacles from sky, virtually, obviously, and then there would be an aggregation of those little obstacles to form bigger obstacles that serve the efficiency of the flow. And then what we find is that there are certain kind of designs that result. Among them, the zigzag shape design or this asymmetrical approach design. Does anybody have an idea why this happens? No, basically, if there's too many people pushing towards the exit, that would actually obstruct the flow. We'll see that later on. And so by reducing the pressure on the people at the door, we would actually improve the outflow, right? And so both the zigzag shape design and the asymmetrical design will absorb the pressure from behind. And that's what improves the situation just at the narrowest bottleneck point, okay? And that can actually be used also to improve architectural designs. For example, elements of soccer stadia or some other stadia, where in many cases, you know, after the game or when an evacuation has to be made, people would push and maybe fall. And that can be very dangerous. And in order to avoid critical pressures building up, it's good to have such a zigzag design, which basically breaks down the pressure into under critical levels of pressure if it's done well. Now, in the meantime, those models that have first been really purely theoretical have found their way into application. So there are many commercial software programs that are now using models like the social force model that I've shown you. And it's possible to simulate large-scale scenarios also of intermodal traffic and trains, buses, taxis, trams, some of them even coupled with logistics. Some people use it in order to plan scenarios for large-scale events, Olympic Games or whatever. And it has been really a useful tool in order to assess possible problems and how to avoid them. But we can say that basically the entire field has gone through different phases. It has started with kind of hypothetical models that were simulated in a computer to reproduce some stylized facts. Then empirical data were gathered in order to calibrate those models. Then experiments were made to test, calibrate, validate, and improve models. And in the meantime, it's an integral part of certain fields of engineering, right? So also social science has found, together with physics and computer science and engineering,